Hi everyone, I'm Ricardo Salazar and happy to share our work on automated feature engineering for algorithmic fairness. This is a joint work with Felix Neutatz and Ziawasch Abedjan. Two people go to a credit institution asking for a credit. These two people share similar characteristics with respect to features that are important to get a credit approved, such as income, years working, or type of contract. Nonetheless, one of these people belongs to a minority with respect to a sensitive attribute, such as nationality, gender, or sex. The credit institution has trained a machine learning application without including any sensitive information to get credits granted or approved. The credit institution has granted the credit of the person that belongs to the majority, while has rejected the credit of the person that belongs to the minority. So now the question is, how can we assess if the machine learning application is being fair or not? To solve this problem, Capuchin, the state-of-the-art, proposes a horizontal approach. The idea is to add and remove tuples to remove the bias of the training set based on a feature categorization by the user. So the user categorizes features into admissible, inadmissible, and sensitive. Admissible features represent features that the user considers could be influenced by the sensitive feature. On the other hand, inadmissible features represent features that could be a proxy to the sensitive feature. Instead, we propose a vertical approach that uses feature construction to enrich the feature vector. Our system FairX, short for Fairness Explorer, receives a biased dataset from the user and also the feature categorization. Optionally, the user can choose a machine learning classifier and can decide the weights for the objectives. Then we construct new features based on the original ones without excluding the sensitive and inadmissible features. In a second, I will show you how we construct new features with different operators. Then we explore interesting feature sets with respect to accuracy and fairness. Last, we compute the Pareto front of optimal solutions based on all the feature sets that we visited during the feature set exploration, and we return one unbiased dataset to the user. Our approach has three main challenges. First, accuracy and fairness are competing objectives. Usually, accuracy benefits from learning more information, while fairness benefits from a small subset of features. Second, how can we generate these new features that can replace existing inadmissible features in a feature representation? Third, how can we efficiently traverse the exponential space of the feature transformations? To construct new features, we apply feature construction operators proposed originally by ExploreKit. The idea is to recursively apply unary and binary operators to get new constructed features. In the unary operators, we have normalizers, such as min-max scaling or log scaling. We also discretize numerical features and apply one-hot encoding transformation for categorical features. In the binary operators, we have the basic arithmetic operators, and we also have high-order aggregators. Now, I would like to show you an example of how can a constructed feature reduce bias and enhance the classification task. In the adult dataset, the classification task is to predict if someone will make more than $50,000 per year. The reported income for married individuals is the income of the household. Moreover, there are more married males in the sample than females. Therefore, including marital status in the feature representation will result in bias against the sensitive group, which in this case is the female category. When we have a look at other admissible features, such as work class, we see that there are categories within this categorical feature that show a more balanced distribution between females and males. Moreover, we observe differences in the mean and standard deviation between the classes with respect to the proportion of instances that are labeled as work class equals federal government. So the question is, can we reduce bias combining inadmissible and admissible features with a balanced distribution between sensitive and non-sensitive group? In this figure, we can observe the values of the new constructed features for the different categories of marital status. The new constructed feature combines the standard deviation of the proportion of instances that are labeled as work class equals federal government grouped by marital status. As you can observe, the distribution of the values of the new constructed feature is balanced across the different categories of marital status. Moreover, when we have a look at the probability of these values for being classified as having more than $50,000 per year, we see that this constructed feature also enables class separability. As you can observe here, lower values have a larger probability of being classified of having less than $50,000 per year, while larger values have more probability of being classified as having more than $50,000 per year. During our research, we found that multi-objective feature selection approaches, such as the genetic algorithm NSJ2, got stuck in local optima, and usually one of the objectives tend to dominate over the other, given the large feature search space. Thus, we had the idea of exploring interesting feature sets in a two-phase approach. So our approach starts with the constructed feature set ranked increasingly by description length. Description length here refers to the complexity of the constructed features. It summarizes the number of raw features and transformations involved in a constructed feature. By doing this, we weigh more features that are simpler over features that are more complex. This will help explainability. So we start performing forward selection to add features that increases accuracy. After the first phase has finished, we have a subset A that optimizes accuracy. With the subset A, we start the second phase, which optimizes for fairness. And for that, we perform backward selection, removing features. If by doing this, we increase fairness. We also perform here floating, but floating here refers to adding a feature that was removed. If by doing this, we will increase fairness. At the end, we can compute the Pareto front of optimal solutions, since we evaluate both objectives in all the features that we visited during both phases. To guarantee that the fairness constraints are met, and inspired by Sexo, recently proposed by Galotra and others, we propose a variant of our two-phase approach. The idea is to remove the constructed features that could potentially leak information from the sensitive and the inadmissible feature into the outcomes. For that, after the first phase, we filter the subset A using Sexo such that we remove those constructed features that potentially leak information from the sensitive and the inadmissible, and then we continue with the second phase as proposed. One of the main challenges of our approach is scaling feature engineering. For scaling feature engineering, one has to scale feature construction and feature selection. To scale feature construction, we prune algebraic equivalent features. We also parallelize the construction of features. And for scaling feature selection, we perform training parallelization, and we also parallelize cross-validation. We also apply a speculative evaluation to parallelize parts of the algorithm that could be potentially parallelizable. To test our system, we use 4 datasets that are known for showing bias against certain groups of people. Moreover, we use the traffic dataset to observe how our system scales with a large number of rows and large number of original features. We compare our system against 4 fairness-aware methods, and we also use the state-of-the-art multi-objective feature selection approach, NSJ2, to compare with our two-phase approach. Furthermore, we evaluate 9 measures, 1 measure for accuracy, the F1 score. We use 7 measures for fairness, and we also compare runtime. We perform 7 experiments, but because of time constraints, I will focus today on the effectiveness results. This figure summarizes the accuracy results for the other dataset. We compare our system against the state-of-the-art Capuchin, and we also use the drop approach, which excludes from the feature representation the sensitive and the inadmissible features. We also compare our system against the state-of-the-art multi-objective feature selection approach, NSJ2, and we also compare against the original feature representation, which doesn't exclude any feature from the representation. As you can observe, both of our proposed methods achieve higher accuracy than the state-of-the-art and the dropped approach. Moreover, our proposed approaches achieve similar or higher fairness compared to the state-of-the-art and the dropped approach. Nonetheless, our system has a larger runtime. To conclude, I would like to underline 3 things. First, feature engineering is a viable alternative to horizontal preprocessing to ensure high fairness and high accuracy. Second, we can generate new admissible features by generating nonlinear combinations of features. And third, we can scale our approach to around 7,500 new constructed features by pruning and parallelization. Thank you.